So, apparently time is broken. So let's see what all that hubbub's about. Joe Scott.
In March of 1949, the British astronomer Fred Hoyle appeared on a BBC radio show talking about various theories of the universe. Hoyle was a believer in the steady state model of the universe, meaning the universe had no beginning or end, it always was, and always will be. But a new model had been gaining in popularity for a couple of decades, one where the universe did have a beginning, that it started from an infinitesimal point and expanded outward from there, and continues to expand to this day. And when talking to the interviewer about this idea, he kind of flippantly referred to it as that Big Bang idea. And the name stuck. Yes, ironically, the Big Bang was named by somebody who doesn't believe in the Big Bang. And one of the reasons that Hoyle and many other people at the time didn't take this idea seriously was because one of the people who was behind this Big Bang idea was an astronomer and mathematician named Georges Lemaitre. More about him in a second. Astronomers knew the universe was expanding as far back as 1912 when Vesto Slipher first measured the Doppler shift of a spiral galaxy that suggested that it was moving away from us. Later scientists like Alexander Friedmann and Edwin Hubble refined this idea, and they found further evidence that the universe was expanding. But it wasn't until 1931 that Lemaitre became the first person to kind of look at that and say, now hold on a second. If the universe is expanding, then that means that it used to be smaller than it is today. And if you go back far enough to the very beginning, that means that it would have shrunk down to an infinitely small point, which means the universe had a beginning. Now, all of this sounds reasonable enough. The problem is that Georges Lemaitre looked like this. He was a Belgian Roman Catholic priest, and yeah, this whole idea that the universe had a beginning, that it began with an explosion of matter and energy out of completely nothing, sounded suspiciously biblical.
Yeah, I wonder why that is.
Let there be light and all that. Over time, as our telescopes have become more and more powerful, we've been able to see further and further back in time to the earliest galaxies, and Lemaitre has been proven more and more right.
Yep.
But actually, the general acceptance of the Big Bang Theory is shockingly new. It wasn't really until the 80s that it was really and truly embraced by scientists. But still, the Big Bang is messy. And a lot of theories have been put forth to explain it, many of which I've covered on this channel. And there are still people who think that maybe there is a steady state explanation for the universe. One of those explanations is called the causal set theory of the universe. And it's pretty solid.
I've heard of this one.
Mathematically, anyway. And it could explain a lot of other vexing questions about reality. So, let's talk about it.
Yeah, because I don't remember. I've just heard of it.
All right, so I'm going to start by
about
issuing my standard disclaimer for videos that talk about big cosmological questions, especially ones that rely on advanced math to make sense. Joe Scott is not a mathematician or a scientist. He is merely a science communicator with a giant forehead who finds these topics interesting. Please consider this video as a jumping off point for you to look further into this topic through far more reputable sources than a guy who graduated from a state college with a radio, TV, film degree. As always, links are down below. So, like all of these big cosmological mystery topics, it all starts with the whole divide between quantum mechanics and general relativity thing. You guys are smart and already know this, so I'll keep it short, but quantum mechanics basically describes fundamental forces, the behavior of particles like atoms, electrons, almost everything in molecular and submolecular realms. Whereas general relativity underlies our understanding of space-time and gravity. It treats gravity as a curvature in space-time created by mass. But general relativity and quantum mechanics operate with very different rules, and physicists have been trying to bring these two theories together for decades. There are four fundamental forces of the universe, and those are gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. And gravity is only one of these forces that is not carried by a particle, at least not one that we found yet. So scientists have been searching for a theory of quantum gravity to solve for this problem, especially around singularities like black holes, because that's where general relativity pretty much breaks down. And another singularity that tears general relativity a new one is the Big Bang. So yeah, to figure out quantum gravity is to figure out nothing less than the beginning of the universe. And over the years, physicists have attempted this in a few ways. One of which is string theory, which is the idea that reality consists of infinitesimal vibrating strings that are smaller than atoms, electrons, quarks, anything you can imagine really. And according to string theory, when the strings vibrate, twist, and fold, they produce effects in several dimensions, and then we interpret that as everything from particle physics to gravity. Then you have quantum loop gravity. This is a theory that's concerned with the quantum properties of space-time. In other words, in this theory, space-time is quantized, or built out of discrete chunks. Like imagine zooming into space-time. According to quantum loop gravity, it wouldn't be a smooth motion. It would stutter from one space-time pixel to another. Time wouldn't move continuously. It would work in quick little ticks of a discrete clock. And this new theory kind of expands on this idea. And yeah, it's called causal set theory. In this theory, kind of like quantum loop gravity, space-time consists of discrete elements, but these are called events that are related to each other through causal relationships, meaning basically one event causes the next to happen, and then the next, and the next, and so on. Like if you can imagine a collection of dots on a piece of paper, and then each dot represents an event in space-time. The lines that connect them represent the causal relationships between those two dots, and if that event causes another event, then another line will form, and so on. And this sort of lattice work of connections between the events is known as a causal structure. Now, of course, if you're talking about the tiniest discrete chunks of space-time, you have to measure them in the tiniest measurements that we know of, and that's Planck length and Planck time. So with causal set theory, Planck length and Planck time represent the smallest possible distances and times between space-time events. But anyway, you get the idea. In causal set theory, space-time is granular. But what does that mean? What that means is that singularities can't happen, because the chunks of space-time can't get infinitely close together. If there are no singularities, that means there was no Big Bang. The universe has always existed, and time has no beginning. Steady state, baby. Now, there's an important thing to remember about this theory, and that is that we have no proof. We haven't found evidence of these tiniest causal units, which are called cosets, by the way. It's kind of like string theory. We've never found the strings, but the math checks out. Same with causal set theory. It's a mathematical construct. And there's two things I can tell you about the math in causal set theory. One, it works. Two, it's way over my head. So let me explain it with a bunch of words that I found but don't understand. Okay, so causal set theory at its core is based on a mathematical concept called partial order relation. This is used to describe a set of events that have a cause.
So science is just a bunch of math based on math based on math. That's what I'm getting from this video.
And effect relationship with each other. Causal set theory builds on top of partial order relation by defining a set of axioms, which are rules for how it all works. They basically define the essential properties of the causal structure, which I talked about earlier. So one of these axioms is a requirement that the partial order relation be acyclic. This means there can't be any loops between the causal relationships between events. Another axiom requires that the partial order relation has to be locally finite, which ensures that the causal structure is not too dense or sparse. There's obviously way more to it, but yeah, it's math based on partial order relation. But if you want to talk about the elements of the causal set itself, the cosets, we can refer to a paper by Professor Emeritus at Syracuse University, Raphael Sorkin. He describes cosets as point events that carry information, saying, quote, "For some pairs, x, y, of elements, not for all, we have the information that x comes before y, or in other cases that x comes after y. Physically, you should think of this ordering as a microscopic counterpoint of the macroscopic relation of before and after in time. For some events, we know that they take place after certain other events." He goes on to explain that the word causal comes in because we say that an event is later than another event if the latter could exert a causal influence on the former. Another way of describing it was laid out by Professor Samadi Surya in the journal Living Reviews in Relativity, saying, quote, "Causal set theory is deeply rooted in the Lorentzian character of spacetime, where a primary role is played by the causal structure poset. Importantly, the assumption of a fundamental discreteness in CST does not violate local Lorentz invariance in the continuum approximation." Hang on a second. Yeah.
I didn't
Now,
like
what all that means,
That was weird.
to my understanding anyway, is that causal set theory works with Lorentzian geometry. This is what uses light cones to describe the geometry of light traveling through spacetime. You could say light cones are to Lorentz geometry what a circle is to Euclidean geometry. This means that cosets can be mapped onto Lorentzian light cones. And what's cool about that is using this mapping, we can study the implications of spacetime's discreteness and how particles behave at high energies or the properties of black holes. So there's a reason why this whole approach is popular to some physicists. So there was a paper written on CST called "If Time Had No Beginning," and in it the authors talk about how in order to explain physics before the Big Bang, we kind of have to turn to quantum gravity, which we still haven't quite cracked. But they argue that using a causal set approach fixes that. It doesn't have to explain the singularity because there is no singularity. This, of course, raises the question of how can there be passage of time if there's no beginning to it? Well, they suggest that time can be explained in CST through the process of spacetime growth. Or, as the paper's co-author Bruno Binto told Live Science in 2021, quote, "A huge part of the causal set philosophy is that the passage of time is something physical, that it should not be attributed to some emergent sort of illusion or to something that happens inside our brains that makes us think that the time passes. This passing is, in itself, a manifestation of the physical theory. So, in a causal set theory, a causal set will grow one atom at a time and get bigger and bigger." Okay, but what about all those observations I talked about at the beginning of this video that point to there having been a Big Bang and a universal expansion? Well, their explanation is to say that basically from time to time in this infinite expanse of space-time, Random fluctuations in energy could sort of merge into an explosion of energy and matter, kind of like a rogue wave in the ocean. Meaning, if you could see for infinity in this vast expanse over infinite space and time, you just see universes bubbling up in this endless ocean of quantum space-time foam. But because of the speed of light, none of them would be able to reach any others, and none of us would ever know that any of these other universes were there. Kind of like a steady-state version of the multiverse. Now, all of this sounds bonkers. But I mean,
Okay.
every theory about
Okay, so I got it. I got it now. So it took 10 minutes to say that there are possibly these sets of universes just, way, way, way far apart from each other. So far that we can't detect them. Probably, like, to us would be infinity. Never be able to reach them. Who knows? But yeah. I don't know why I needed 10 minutes to explain that.
the beginning of the universe sounds bonkers. Like, this isn't the first theory that I've heard talk about the idea of quantum space-time foam bubbling up universes. I mean, you could go back to my video on the ekpyrotic universe theory, where the Big Bang is explained as a breakaway piece of quantum membrane that breaks off and smacks into another quantum membrane like a wet towel. That's how they explain it, like it's a wet towel hitting another universe in the face. Seriously. Yeah, and pretty much every explanation for the beginning of the universe, the mantra still seems to be, give us one miracle and we'll take it from there. So I don't know, maybe it's not so weird that the most accepted theory so far was created by a Roman Catholic priest. But right now, like I said, this is all math. It all still needs to be proven experimentally, and to my knowledge anyway, there are no experiments in the works to prove this just yet. So, we'll see. So links are going down below for anybody who wants to dive further into this or maybe actually understands this way better than I did. But you guys tell me, what does that mean to you, to be in a universe with no beginning or end? You know, does it make you feel part of...
I know the comments are going to be like, oh, this is my basic understanding that the Earth revolves around... Yeah, there's going to be a bunch of people who think they know what they're talking about. Like, they know what's going on, even though they're not... They don't have a name to them, and nobody knows who they are. You know what I mean.
something infinite? Does it not matter because you got to get up and go to work tomorrow anyway? Talk about it in the comments. By the way, there is one upside to a steady state universe, and that's the fact that in an infinite, never-ending universe, you'd have more time to craft delicious, healthy meals with today's sponsor, HelloFresh. Granted, your lifespan would still be the same, but you might live longer if you ate healthier. Which you can totally do with HelloFresh. They've got a new fresh and...
Alright. Well, did I learn anything? I learned that the name of the theory of universes being next to each other throughout the infinite space-time was causal set theory. Was that that's gonna be stuck in my mind as that. So if it's not, oh well.